Hello and welcome back. In the previous video, I introduced the concept of vectors, and we talked about different ways to represent vectors, whether it was in component form or as a magnitude and direction. We also talked about how you go back and forth between these two representations, and then we also talked about how you can graphically represent a vector as an arrow. Now, in this video, I want to talk about just vector arithmetic. So how do we do basic operations like multiplying something by a vector or adding two vectors together? So I want to start with just multiplication by a scalar. So remember that when we talk about vectors, we say a scalar, that's like a normal number, like 2 or 3 or something like that. So if I have a vector A and I multiply it by a scalar C, the way that we evaluate that is that we just take both components. We take the x component and multiply it by c, and you take the y component and multiply it by c. So it's very straightforward. It's just like distributive property. Now there are two important things to know about multiplication by a scalar. The first is that the magnitude of the new vector is just going to be equal to the absolute value of c, the scalar that you multiplied by, and times the magnitude of the vector that you started with. Okay, so let's go ahead and prove this. This is pretty straightforward. We'll just calculate the magnitude of the vector c times a. So remember, the way we calculate a magnitude is we take the x component and we square it, and we add it to the y component squared, and then we square root that whole thing. So the x component of c times a, remember that was on the previous slide, right? We take c and we multiply it by the x component of vector a. So the x component is c times, sorry about that, lowercase a, x. That's the notation that I've chosen to use for the components of vectors. So we take that x component and then we square it. And then the y component is just going to be c a sub y squared, and now we need to square root that entire thing. Now notice that I've got c squared in both of these two terms, so I can factor that out. So I can write this as c squared times ax squared plus ay squared, of course square root still. And then if I want to, I can write that as c squared square rooted times the square root of ax squared plus ay squared. And now notice that this thing over here, this is the magnitude of vector A, and this thing here is the absolute value of c. So we can see that in fact the magnitude of c times the vector A is just the absolute value of c times the magnitude of vector A. The other thing to know about multiplication with the scalar is that the direction of the vector is always going to be one of three things. So if I multiply the vector a by a positive number c, so if c was like 1 or 2 or something like that, then the result is going to point in the same direction as vector a. So for example, if I have vector a, let's say it points like this, then 1/2 times a might look something like that. 2 times a would just be twice as long, but it's going to point in the same direction. Okay? Now, if I multiply the vector a by a negative number, like say -1, then the result is going to point in the opposite direction. So for example, -2 times a would be something like this. Okay, so it's going to point in the opposite direction as the vector a. Now the last one's a little bit tricky. It's a bit of a trick kind of a scenario. If we multiply the vector a by 0, then what we get is something called the 0 vector. And this is something that has no direction. So it kind of contradicts that definition I gave at the very beginning when we first started talking about vectors. I said that a vector was something that has magnitude and direction. Well, this thing has magnitude, it's 0, but it doesn't really have direction anymore. So a times 0, or 0 times a, that's just this 0 vector. We put a little arrow above the number 0 to represent that this is a vector. Okay, so it does have components, it's just that both of the components are 0. Now that's how we multiply by a scalar. How do we add or subtract vectors? Well, It's very simple. So if I have a vector A and I add this to a vector B, all you do is you just add like components. So the x component of this is going to be the x component of vector A plus the x component of vector B. And the y component will be the y component of vector A plus the y component of vector B. Similarly, subtraction, we do the same thing. So we have the x component of vector A minus the x component of vector B, and then the y component of the difference is going to be the y component of vector A minus the y component of vector B. So how do we graphically interpret the sum or a difference of a vector? Well, basically all you need to do is place the two vectors head to tail to take the sum. So if I have, say, some vector A, and I want to add it to a vector B, I place vector B at the head of vector A. So now they're placed head to tail like this. And then the sum, the way you get this, is you draw a vector. It starts at the tail end of vector A, and it points to the arrow of vector B. So it's going to point like this. So this is vector A plus the vector B. Okay? So the sum, you just place the vectors head to tail, and then you draw an arrow from the beginning over to the end of them. So that's addition. How do we handle subtraction? Now, I think the easiest way to think about subtraction is if I have vector A minus vector B, I could write this as vector A plus minus 1 times vector B. Those are the same thing. Okay? And remember, minus 1 times the vector B, that's just going to be the vector B, but pointing in the opposite direction. So if I had, say, some vector A, like this, and I had a vector B, say it looks like that, then A minus B is going to be A, and then minus B would point like this. Right? It's going to point in the opposite direction as vector B. So vector B pointed up and to the left, minus B will point down and to the right. And now I can just take the sum like normal. So I start at A and I go to B, so it's going to be A minus B here. Now, there's another way that we can do this. If I draw vector A, and then I draw vector B so that they're head to tail, so this is vector A and this is vector B, then A minus B points from B to A. Right, so we can see that this vector here is really the same thing as what we have here. In fact, I can see that if I draw vector B over here, that's going to look like this. Right, if this is minus B, this is B here. And now we can see that this is also going to be A minus B. Okay, and in fact, we can see that this forms, had I drawn this a little bit better, it forms a little parallelogram. So that's just what this slide is saying here. If I want to graphically think about the difference, you place the two vectors tail to tail, and then you draw a line that starts from the vector that you're subtracting to the vector that you're subtracting from. So if I want to do A minus B, I start the arrow at B and I point it towards A. So I start at the one that I'm subtracting B, and it points to the vector that I'm subtracting from, and that's A. Another way to remember this is that it's going to be backwards. Okay, so if we have A minus B, the vector starts at B and it points to A. So if you place them tail to tail, you're going to start at B and go to A. So let's just do some practice with addition and subtraction of vectors. And I want to start out with just the graphical, because this is a little bit easier. So here I've got a whole bunch of vectors, and we're basically just going to pick out which one is going to be equal to these different examples here. So here I say, what is E plus F? So E is this one here, it points up and to the right. F is this one here, it's pointing to the left and up. So E plus F, that's going to be, here's E. F looks like this. So E plus F, I didn't draw that very well, that would point up. So we can see that that's vector C. Next one is F plus G. Maybe I'll just use this. So this is our F here. G points down and to the left. So we can see now that the sum of these two vectors points to the left. So that's vector A. This next one says A plus E. So here is A. E is pointing up and to the right. So we can see now that the sum of these two looks like this. It's pointing up and to the left, so that's F. Now this one says F plus H. So this is a little bit of a tricky one. Here's F. H is pointing in the opposite direction as F. So if I took the sum of these two vectors, then I'm going to get 0, right? So I have the 0 vector. So anytime when you add two vectors, if the arrow end, the head end of the last vector is where you started from, then the result of that is the 0 vector. So another example, we've got E plus F plus D. So here's E. F is going to point up like this. D is pointing down. So if I add all those together, that was F and this is D. Again, we can see that I'm going to wind up ending where I started. So this is also the 0 vector. And then we'll do one example of subtraction. So if I have E minus F, again, I think the easiest way to handle this is E plus a minus F. So here, F points like this, so minus F would point down like this, right? This is going to be minus F. So E minus F, or E plus a negative F, just points to the right. So we can see that that is vector B. So that was some examples of graphical addition and subtraction, but most of the time we're going to actually need numbers. So this is a more realistic example. It says vector A has a magnitude of 5 meters and points east, and vector B has a magnitude of 13 meters and it points 22.6 degrees west of north. And we're asked to find the components of vector A plus B. So I think anytime we have a problem with vectors, it's always a good idea to just draw this so we have kind of a picture in our head of what this looks like. So vector A, remember, so to add, we put the vectors head to tail. So vector A is 5 meters and it points east. And then vector B is going to point, let's see, west of north. So I can put this down here. So we've got vector A. Looks something like that. And then vector B, see, this is 22.6 degrees west of north. So let me think about that. So this is north and this is east. And this is west here. Oh, I don't need a vector there. This is west. So west of north, right? That means I'm measuring my angle like that, right? So I'm going west of north. So 22.6 degrees west of north, and this is 13 long. So it's maybe going to look something like this. Okay, and this angle down here, this is 22.6 degrees. And then this is going to be my sum. This is A plus B. So this is kind of a picture of what I think this is going to look like. So let's go ahead and actually do the addition. Now remember that I said that the way we add two vectors, so if I have A plus B, this is, I take the x component of A and I add it to the x component of B, and then the y component, I take the y component of A and I add it to the y component of B. So obviously I'm going to need to be able to decompose vectors A and B. I need to know what the x component and the y component of vector A is, and I need the x and y components of vector B. So anytime you have to add or subtract vectors, you always have to write those vectors in component form. So if we look back at the previous slide, I said that vector A points east. So if I say that east is my first component, let's say north is my second component, so I'll say north and east are positive. Well, then vector A, that's easy, right? Vector A, it's just going to be 5 meters, comma 0 meters. Because there's 5 meters in the east-west direction and 0 meters in the north-south direction. So let me write that down. So vector A 5 meters, comma 0 meters. Now what about vector b? So vector b, let me draw a picture of that again. This angle was 22.6 degrees, I think. Let me double check that. Yep. And the magnitude of vector b was 13 meters. So looking at this here, I need to find the components that are east-west direction and north-south direction. So the first component is the east-west direction. We can see that vector b has a component that's in the west direction, so I'm going to call that a negative direction. And if I want to find this component, notice this is opposite the angle 22.6, right? So this is the component of b that's west. This is the component of b that's pointing north. So I'm going to have minus b west, and then the component of b that points north. So the west component, right, it is opposite the angle theta, so I can say that sine of theta, the sine of 22.6 degrees is opposite divided by the hypotenuse. Okay, so solving for the west component, we see it is going to be minus the magnitude of vector b times sine of 22.6 degrees. And the y component, well, now this is adjacent, so it's going to be the cosine. Right? So we'll have the magnitude of vector b times cosine of 22.6 degrees. Give myself some more room there. So now if I plug these things into a calculator, so I take 13 and multiply it by sine of 22.6, then I get minus 5, or sorry, minus 13. So we have minus 5 meters is the east-west component of vector b, and the north-south component will be 12 meters. So that's vector b, and over here we have vector a. So now if I want to take the sum of these two things, remember I take the x component of vector a and I add it to the x component of vector b. So we have a plus b is going to equal, so we'll have 5 plus a negative 5, so that's 0. And then for the y component we'll have 0 plus 12, so we'll have 12 meters. So actually I drew this pretty good in the previous picture, right? It's all pointing in this vertical direction. So we can see that our vector is 0 meters in the east-west direction and 12 meters in the north-south direction. So just 12 meters north. So let's look at another example. This one says, it asks us to find the magnitude and direction of a plus b, where a has a component of 2 in the x direction and 0 in the y direction, and b has a component of 1 in the x direction and 2 in the y direction. So this is pretty easy to do the sum because they were already given to us in the component form. So right away we can write down that a plus b is going to be equal to 2 plus 1, that's the x component, and the y component will be 0 plus 2. So this is 3, 2. But the problem asks us to find the magnitude and direction. Okay, so the magnitude of this, that's pretty straightforward. We'll just use the formula. So the magnitude of a plus b, remember we take the x component and square it, so we get 3 squared plus the y component squared, and then you square root all of that. So here we've got 9 plus 4, so this is the square root of 13. And if you plug that into a calculator, you get 3.6. So that's the magnitude. Now what about the direction? So let me go ahead and write this down. A was 2, 0. And what was b? B was 1, 2. So anytime you have to find direction, remember it's a very good idea to just draw a picture of what we're looking at. So A has 2 in the x component, 0 in the y. B had 1 in the x component and 2 in the y. So 1 in the x direction, 2 in the y. So B looks something like this. So A plus B looks something like that. Okay, so probably the easiest way to do this is this angle right here. We know that this component, right, this is the x component of A plus B, and that's 3. This is the y component of A plus B, this is 2. So looking at this triangle right here, if I want to find the angle theta, right, theta is going to be equal to, so I know the opposite, I know the adjacent, so I should use arctan. So it's going to be the arctan of 2 over 3, and that's equal to 33.7 degrees. And remember, anytime you describe the direction of a vector using an angle, you always have to say how that angle is being measured. So looking over here at this picture, if this is the y direction, and this is the x direction, this angle is going to be, we could say it's, counterclockwise from the positive x-axis. Right? So I'm going like this. That's how I'm measuring my angle. So let's look at one last example. This example says Western Albemarle is located, let's say, 5 miles, 36.9 degrees north of east from your home. And Kroger's is 13 miles, 22.6 degrees east of south from your home. And the question is how far and in what direction would you need to drive to go from Western Albemarle to Kroger's? I guess assuming that we could just take a straight path. So this is a real word problem here. We're going to have to interpret this in terms of vectors so that we can solve it. So what I'm going to do is I'm going to use a vector to describe the position of Western, and I'll use a vector to describe the position of Kroger's with respect to your home. So this is the direction you would travel from your home to get to Western Albemarle, and the direction you travel to get from your home to get to Kroger's. So let's call, I guess, this point will be your home. Or no, maybe I should move this up a little bit. So Western is 5 miles in a direction that is 36.9 degrees north of east. So let me just put a little axis here. This is north, and this is east. So we're going to go 5 miles and 36.9 degrees north of east. So that looks something like this. And I'm going to call this vector W, since it points to Western. Okay? Now the other vector, this is the one to go from your home to Kroger. This is 13 miles in a direction that's 22.6 degrees east of south. So east of south, this is south, that means we're measuring the angle like this. Okay, so this is going to be 22.6 degrees east of south. So probably something that looks like this. And I'll call that K. So this angle right here, this is that 22.6 degrees. And the other one, this is going to be 36.9 degrees. All right, now the question is how do I go, let's see, where am I going from and to? So I'm going from Kroger's to Western. So if I wanted to do that, I would want to travel, let me change the pen color here. I want to travel in this direction, right? So I'm going from Western to Kroger's. So this is what I want to know. So I'm going to call this WK, the vector WK. I'm going from Western to Kroger's. So what is this in terms of vectors? Like, how do I write this as a vector equation? Well, let's see. Remember that if I place two vectors tail to tail, and I draw my arrow from one to the other, that's a difference between the two of them. So if you're like me, you can't remember whether it goes from, let's say, W to K or K to W, which one that is. Remember that you can always use the difference between two vectors is one vector plus the negative of the other. So let's see, what is W minus K? What would that look like? So W minus K, W points upwards like this, minus K, K points down like this, so minus K would point up like this, right? So just looking at this, W minus K, here's W, here's minus K. Obviously that's pointing in the wrong direction. That's going to be pointing up and that's not what I want. I can look at this picture down here and see that the vector is pointing down. So we can see that WK, that's equal to K minus W. So this is what the question is really asking me to do. It's asking me to take K and subtract W, and then it's asking me to find the magnitude and direction of that. So remember that when we take this sum or difference of a vector, we need to write these vectors in component form. So the way I do this is I take the x component of k minus the x component of w, and the y component of k minus the y component of w. So I need these vectors in component form. So let's just go ahead and do that now. I've got these already drawn really nicely here. So looking at w, right, we can see that the east-west component, right, that's this direction right here, that is adjacent to my angle, 36.9 degrees. Right, so the east-west component is going to be cosine. So I'll take the magnitude of w times cosine of 36.9 degrees, because it's adjacent. Right, and then the north-south component of this, that's opposite this angle, 36.9 degrees. So I'll use sine. So I get magnitude of w times sine of 36.9 degrees. Okay, and since this is east and north, remember my convention is always the east is the first component, the east-west is the first component, and east is positive. North-south is the second component, and north is positive. So both of these are positive. It's pointing east and north. So now if I plug this into a calculator, right, so if I take 5 times the cosine of 36.9 degrees, I see that that is going to be, I think, 4, and this is miles here. And then the other component will be 3 miles. So we can do the same thing now with this vector k over here. Now remember this 22.6 is being measured east of south, so it's this angle right here. So the first component, this is the east-west component, and we can see that this is pointing east, so it's going to be positive. It's going to be the magnitude of vector k, and because this is opposite the angle, 22.6 degrees, I'm going to use sine of 22.6 degrees. And the north-south component, right, we can see that this is pointing south, so we call that negative. And we can see that this is adjacent to the angle 22.6 degrees. So this is going to be cosine of 22.6 degrees. So now if I take this and I plug this into a calculator, so I take 13 times the sine of 22.6, I see that that's 5 miles. And the other component will be minus 12 miles. So let me write those down. So I had W was equal to 4 miles, comma 3 miles, and K was 5 miles and minus 12 miles. So now I want to take the difference between these two. So remember that we had this in the previous slide, that W minus K, oh no, I erased it. W minus K, that is, I'm sorry, W minus K. WK is K minus W, right? Remember that you start from the vector you're subtracting, pointing to the vector you're subtracting from. Okay, so it's K minus W. That's what WK is. So WK is equal to K minus W. And so this is going to be, so I take 5 minus 4, that's 1 mile. And I take minus 12 minus 3, so that's going to be negative 15. So this is the vector that points from Western to Kroger's in component form. But if we look at the problem, I said how far and in what direction. So that means I need to rewrite this in magnitude and direction. So again, that's not too bad. The magnitude, the way we get that, we take the x component and square it, we add it to the y component squared, and then we square root the whole thing. So we have 1 mile squared plus minus 15 miles squared, and then we square root the entire thing. And this is going to be pretty much just 15 miles. So now we need to find the direction of this, okay? So let's just go back to this and look at this. So we can see that this vector is kind of pointing mostly down. So again, the way we find the direction is we're going to use an arctan. So we see that theta is going to be equal to the arctan. Let me just kind of draw a picture of what this WK vector looks like. So this is going 1 mile east and 15 miles south. So this vector, this is east and this is south. Our vector is basically going something like this. So it's almost going completely south. So I think the easiest way to do this would be to define the direction in terms of this angle here. Okay, so in this case, the direction that's opposite the angle theta is the east direction, and the one that's adjacent is the south direction. So tangent is going to be east over south. So arctan, we want to take the east component, that's 1 mile, over the south component, that's the 15 miles. So if you plug that into your calculator, the arctangent of 1 divided by 15, that's 3.8 degrees. And looking at this picture here, we can see that that angle was measured east of south. So that's how you would get 2 Krogers from Western. This is probably not at all true, so don't try this. But that's the answer to the problem. You would walk 15 miles in a direction that's 3.8 degrees east of south. And so I think I'll end this lecture there, and I'm not sure, I think in the next lecture we're going to begin talking about kinematics.